Okay, go ahead.
So are you referring to the technique called radiosity? I mean, is that which is used to calculate, it's like indirect, like diffuse lighting, or is it like the more general term radiosity?
Well, so here's the thing. In computer graphics, it's a bit mixed, the term. The issue was that this radiosity technique, I think the paper introducing it was around the same time the rendering equation was introduced. So they didn't have the rendering equation when they introduced that. So it was based on, I believe, heat diffusion literature from physics is what they try to port to graphics. And for heat diffusion, some things are important, and there are assumptions you can make there for, let's say, for the specifics they did, but they try to port this directly to graphics, and then the assumptions remained, which doesn't always work well. But radiosity, as people understand it in graphics, is usually the radiosity formulation, which you can get by doing some assumptions regarding the rendering equation, and then you get the radiosity formulation, radiosity as the radiosity from radiometry. So integrated excitant radiance integrated over solid angle. And that's the formulation, but people usually couple that. So when you say radiosity in computer graphics, they usually understand radiosity with finite elements and usually mesh based. What?
Yes. Yeah. So I was thinking of finite element like radiosity. It's like when I heard it brought up.
Yeah. So there's technically finite elements and radiosity are two different things, but in graphics, people understand the same thing. You can just as fine apply finite elements on the rendering equation itself as so with respect to just radiance, and then it won't be radiosity, obviously. But
I see.
It's just a misnomer that stuck around.
I see. And so I guess the reason why radiosity and the finite element method are used so often, like together, is since radiosity, which is diffuse, indirect lighting. It's like tends to be like of a lower frequency, so it tends to fare better, when rendered by the finite element method.
To some extent, yes. It's also simpler. So, as mentioned, it's just historically developed like that, in the sense that they had the approximation. They didn't have the rendering equation, they had the approximation.
Yes.
So they used that, and then it stuck around. What stuck around as radiosity was actually the radiosity formulation plus finite elements, and usually finite elements that are mesh-based, so let's say triangulations or some tessellation of your scene, with some polynomial functions on those. But in general finite element literature, that doesn't have to be the case. You can use mesh-free elements, let's say Gaussians or whatever kernels, like in the photon mapping. So that's very, very specific to graphics, like this misnomer. And things get muddled because of that, but yeah.
Thank you for explaining that.
Yeah.
And I actually have, and then I also do have one more question. So finite element means I can also, so it doesn't have to be like a triangulation like of the scene, right?
No, it doesn't have
to be. So you could use like a voxelization of the scene or something, and that would also
that would be for volumes. But what I meant is you could see photon mapping as finite element mesh-free finite element solution. So what would you do there? You say, okay, my basis functions are not defined on triangles; they can also overlap. For example, I pick Gaussians for basis functions, and that's it. And then you say, okay, that's my basis function, and then I just write the finite element formulation. And we'll see in the PDF I've prepared that it's exactly the same thing. So how you write the problem, what's called the Galerkin method, it's exactly the same. It doesn't care what basis functions you pick. You can pick whatever. You can pick
Gotcha.
Hertz, you can pick triangles, you can pick Gaussians, you can pick spherical harmonics. You can pick whatever you want, basically.
Okay.
And in Radiosity, they pick something specific, and the book is it discusses that specific thing and specific methods for. And actually, what 6.2? Oh wait, I haven't shared my screen. Let me do that. So what 6.2 and onwards discusses is really the numerical solvers. The stochastic numerical solvers used to solve a linear system of equations. That's it, really. That's so all of these 6.2, 6.3, 6. Whatever. It's basically a different numerical solution to an almost the same linear system. Yeah.
Gotcha.
Other questions? Okay, if there are no more questions, I guess we could start with the summary. So, yeah, why consider radiosity methods? Well, technically, probably nowadays there's not that much reason, but there is a point to be made, and it's that, okay, they compute a word space solution in the sense that you compute the solution of your scene, and then you can pick any viewport and use whatever you've pre-computed to generate an image. So it could be used for interactive stuff. You can think of it as a fancier light map. If you know a light map, then you can think of this as a pre-computing a fancier light map that allows you to store some of the data that of the light data, provided that nothing moves in the scene and the lights do not change. So for static stuff, you can pre-compute, and then you can just walk around and do just a zero bounce trace, and then retrieve the information you want from that. Okay, let's see. So we will see that the radiosity equation is really the rendering equation with the assumption of that all the BRDFs are Lambertian, and that all emitters are Lambertian in the sense that they emit the exact same radiance in every direction. So the first assumption is, okay, we say our BRDF is Lambertian, then the incident and outgoing direction do not matter. You get the exact same thing, so you can define it as a function on the other points. And that would be some constant. For a specific point, that would be, let's say, just whatever you say the color is there. Then, if you do that, you can take out f of x, simply because this is an integration of a solid angle, and there's no solid angle, so you could take it out of the integration, and you're left out with this formulation. Now you can also say, okay, all of my light sources are defined to emit the exact same amount of light in every direction, and they only vary based on the position. So then you drop the theta here, and you're left with emitters that emit uniformly in every direction. Then you take this equation, you rewrite it, and now you see that the theta here on the left is not present on the right, which means, okay, this is not really a function of theta, because once so if we assume that if the BRDF wasn't Lambertian, then you would still have this theta because you have it here. But since the BRDF is Lambertian, you don't have a theta here, you don't have a theta for the emittance, then you also wouldn't have it here. So this is just a function of position. And in the same way, since this is simply a function of position, you have the same thing here, because the direction doesn't matter, because you know, okay, in every direction it is the same radiance. Then you're left with this formulation that doesn't have any directionality dependence except for this here, dy. Let's continue then. From this we'll get to a radiosity formulation. How? Well, let's remember what we saw in chapter 2 from radiometry, that radiosity is defined as an integral of a solid angle of the radiance multiplied by the cosine, and you have, okay, integration of a solid angle. And now let's plug in the fact that our radiance is doesn't depend on directions. Then you get this. You can take it out. You can take out L of x, simply because this is an integration of a solid angle, and there's no solid angle here. It's only here. Then the integral of this is just pi. So we get pi multiplied by the radiance is your radiosity. So you could take the equation here, multiply both sides by pi. So here, here, and I've taken the pi inside the integral here, and then turn that into a radiosity formulation. So this is really the formulation that radiosity, typical, standard, classical radiosity methods solve. So in this formulation you have two assumptions. The first is the BRDF is Lambertian everywhere, and the second is the light sources emit exactly the same amount of light in every direction. Why is this done? As mentioned, so first it was for historical reasons, but you also have the nice fact that, okay, now you don't have any directional information, so you don't have to deal with that. So it's a bit easier to compute maybe, and also to store the data. What you will see in the book is instead of the BRDF here, they have something they call reflectance, which is really pi multiplied by f of x, and then they've taken out this pi and introduced it in the geometric term. Let me show you what I mean. Where is that? Okay. Here? No. Here, they've introduced it and modified the geometric term. I don't want to modify it, because then why modify something when it will just make it different from the rendering equation? So I'm just keeping the f, but you have to remember that for energy conserving Lambertian BRDFs, f of x is between 0 and 1 over pi. And now if you multiply these by pi, so the rho, then rho would be between 0 and 1. Yeah, so this is the formulation that would be solved. So how do we solve that? Well, there's a major problem. Imagine for a second that we actually could compute that at every point. And now to store the solution, however, over infinitely many points, well, that's impossible, at least not without infinite memory. So even if we could compute this exactly and everywhere, we cannot store the solution if we don't have infinite memory, because the surface points are infinitely many. So that implies that we need to do something, somehow to reduce the computation, basically say pick only some points where we want to store the solution. And that's where finite element methods come into play. Basically, we want to take something that's infinitely dimensional and project it into a finite dimensional space. So that's what the finite element formulation will do. And I'm not talking about finite elements as in for partial differential equations. It's just for approximation here. So let's look at what this really means. So what this really means is you take some, where is that? You take some elements, so you have your scene, you tessellate the scene, let's say in even more triangles, and then you say, okay, in each triangle I would pretend that the radiosity is constant. And if the radiosity is constant in each triangle, then I need to only compute the radiosity for as many triangles as I have, because even if in each triangle there are infinitely many points, and otherwise I would have had to store the solution at infinitely many points, if I pretend that in each triangle that I subdivided my scene into, the radiosity is constant, then I only need to store as many coefficients as I have such triangles. So the point here is just to reduce the problem so you can store the solution, even just the solution in your computer. And one way to go about it is to say it's constant, then you get such artifacts. Another possibility is to say, okay, I pick something higher order, so not constant polynomials, but quadratic polynomials. Then you get something a lot smoother, something quadratic. You can also pick other functions. You're not limited to polynomials. You can pick rational functions, you can pick Gaussians, kernels, whatever. Yeah, and it should also be clear that by increasing the number of triangles, or by making these infinitely small, you would get to the correct solution. So if you have infinite memory, you can retrieve the correct solution. What's the comparison to path tracing in some sense, in terms of quality? Well, in path tracing, you usually get noise, and here you get more like a bias. You can also get noise depending on your solver, so your solver can be stochastic, and then you can get, as you can see, some darker regions, then some lighter regions where it should be a lot lighter, let's say, or a lot smoother. But again, the bias is obvious when you split your scene into pieces, at least if you're using low order polynomials on these patches. Just as an example, for example, if you wanted to have, let's say, linear functions inside each triangle, instead of storing just the radiosity per triangle, you would store radiosity at each vertex of every triangle, and then that would generate you piecewise linear functions. So a triangle would you can interpolate linearly over it. If you wanted to do something quadratic, you could also add coefficients. So estimate the radiosity at the edge midpoints of the triangles, then you get 6 coefficients with the vertices, and from that you can construct a quadratic function, etc. So you can go to arbitrary higher orders. Yeah, let's look how this looks formally. Formally, you have your scene, so the points of your scene M, you tessellate your scene into n patches, such that the patches, when you take the union, you get the full scene, and they are disjoint. So if you have two triangles, they never overlap. You use such a tessellation, and then you pretend that in every patch your functions are constant. So the radiosity is constant, the BRDF is constant, and by using, and you can think, even if it were not constant, you can think of these as taking the average inside the patch. So estimating the average. Starting from the formulation that we saw here, we integrate both sides over some patch. We choose a patch, let's say I. We integrate both sides, and then we get this using that relationship. So you just get something that is not defined over infinitely many points. So this is one coefficient. This is, let's say, just a RGB triplet. This is also, and then you have some integral, but we will see how to deal with that integral. Yeah. Questions? Okay, then let's continue with this. So what do we do after that? We have the relationship that B here. So I still haven't substituted this radiosity. I know that inside a patch J, it is equal to Bj. And I can use that M is equal to its union, and then I can use the additivity of integrals to take this as a sum. So the integral over all points over the radiosity is equal to the sum over all patches, and then you have a constant now for the radiosity, just using that. And this comes from the tessellation. Basically, the fact that your triangles are disjoint allows you to write the equality here. So finally, you get an equation that looks like this, where you have a constant, and you know this. You don't know Bi, you don't know Bj. that's what you're looking for. These you know, but maybe you cannot compute the integral analytically. And AI here is simply the area of the patch I. Now, if you do this integration, so we did that integration once just for patch I. Now you can do it for every patch, for patch 1, patch 2, patch n, and you get n equations. And also let's take this term here and call it Fij. We will refer to that as a form factor. Then by using these n equations, you can write this in vector form. So you can write the equations as a vector b, our unknown, equals to the emitted radiosity, this is known, plus a diagonal matrix based on the BRDF, you can see it here, multiplied by the form factor matrix, multiplied by our unknown. Now if you rewrite this just algebraically, you get a solution that looks like that. Now, in practice, you do not have to invert the matrix, this matrix here. You can just use a solver, so you don't have to directly invert it. And such a solver can be a Jacobi solver, a Gauss-Seidel solver, Southwell, conjugate gradient, so anything you can think of that is applicable to the matrix you have. And technically, everything in the book from 6.2 onwards is about what kind of solver they use. And for the most part, they use stochastic solvers. So this matrix here, it's an n by n matrix, where n is the number of triangles, let's say, that you subdivided your scene in. And if your scene is large, and you want a high enough resolution of your solution, then you have many triangles. So this grows very quickly. And for that reason, people usually don't want to store it, even if it is sparse, because some triangles may not see each other, so that may be 0 for some triangles, so then you have a 0 term there. So in most cases, people don't want to store that matrix, so what they do is, while trying to solve this equation, they simply approximate one row at a time. And they do that stochastically, and you can see that in where is that algorithm? For example, in this algorithm, this path 4 here is really approximating through path tracing, you can think, this integral, but at some higher bounce count, so some power of the matrix F. So they approximate one row to be able to do the dot product that you can find in Jacobi. If you haven't seen a Jacobi method, don't worry about that. In a Jacobi method, you basically need to have some vector addition and a matrix vector multiplication. And the matrix here is the matrix F, and you estimate each row, at least with the stochastic Jacobi that they show, but you just estimate it stochastically, and then you perform the dot product. So the dot product would be this part, and here you have some heuristic on choosing how many samples you want to do. And this iteration over I is the iteration over all rows. So it's the matrix vector multiplication. Questions? Yeah, so in practice, this basically concludes everything that radiosity methods, at least as far as constant elements go for this problem. This is really the solution in the whole formulation. The rest is really what kind of solvers you use. And as mentioned, this in here you have different solvers. Then they go to photon density estimation. Now this is a bit different than simply radiosity with constant elements. And to illustrate that, I've prepared some appendix. I won't go into many details into the appendix, but I'll just give the general idea. If you have the radiosity equation, you're not forced to use constant elements. And now I'll show you how you can pick any elements, or alternatively any basis functions. So having the radiosity equation, you can write it in operator form like this. And then you can pick some bases. For example, say you don't want constant functions over triangles, but quadratic. So those would be quadratic basis functions. As mentioned, for quadratic finite elements, it's typical to just take the three vertices of a triangle where you store radiosity, and then the midpoints of the edges, and there you would also compute the solution. And from these 6 points, you can construct a quadratic function. Yeah, so you have this equation, and we will do an approximation. We'll say our solution function is represented through n coefficients multiplied by the basis functions. And here you can see that also these coefficients can be computed as some kind of integral between the actual solution and some part of the basis functions. What's the method about? Well, you want your approximating function in some basis to be as close as possible to the actual solution. So this is the actual solution, this is the approximation that is finite dimensional. What does this mean? You want to find coefficients b1 to bn that minimize, let's say, the L2 norm, so the square difference between the actual solution and the approximate solution. How you do that is, it's called the Galerkin method. It produces you a result like that. So you take the original equation and you can think of it as taking the inner product with the basis functions on both sides. Just as an analogy, where this happened here is we integrated both sides, but with a constant function. So the constant function was 1 over ai here. Instead, here you have arbitrary basis functions. You integrate both sides. So these inner products really expand to what you see here. Finally, you get, once again, form factors as before, just more complex. You get the right-hand side, again, just more complex. So in the previous case, this phi here was 1 over ai. And finally, you get a matrix which is a bit more complex than what we saw before. So just to see that this is more general, you could, as an exercise, take this formulation here and plug in these basis functions. And then you would get exactly the constant formulation that we saw and which is also in the book. So the constant elements formulation is this formulation. So that formulation you can get simply by using these basis functions. It's a b-orthogonal basis. A more natural basis in mathematics is an orthonormal basis, in which case you get the equation for power. So you don't have radiosity anymore, you have power, and they actually have that also in the book. So the power formulation, though they do not motivate it, it's basically multiplying by the area you basically multiply your radiosity equation simply by the area, and then you get the power. But the power equation is in some sense more natural, since your basis functions are the same. So the primary basis function and the dual basis function are the same. So you don't have a basis that is b-orthogonal. If you don't know what a b-orthogonal basis is, it doesn't matter much. And once again, then you get I've written the matrices that you need here. So this is simply for people that are more mathematically inclined, if you want to see, okay, how the whole thing works, and if you want to derive, for example, if you want to implement radiosity with, say, cubic functions or quintic functions or Gaussians, then you can use the derivations here. These derivations are not in the book, though. Now, just to reiterate that which I guess goes further with the questions that was asked in the beginning of the discussion, is that the finite elements methods do not have to be applied to the radiosity formulation. So you do not really have to assume that every surface is diffuse and that every emitter is diffuse also. You can just as well take the rendering equation and apply finite element methods. The only difference there is that your basis functions would now have a directional component, and for instance that could be spherical harmonics if you want. So your basis function would be some combination of spherical harmonics defined over different points of your elements or whatever. Then your approximation, once again, you would have n coefficients multiplied by the basis functions. We do the same, we want to achieve the same thing. We want to have the error be minimal between our approximation and L. So we want to find the best coefficients. We take the original formulation of the rendering equation operator form, inner product with the n basis functions. You rewrite that, then you get the matrices, and I've written explicitly the matrices that you get. And technically, photon mapping falls into this latter category with basis functions that are the kernels that you pick for the photon mapping. In practice, you do not really compute these matrices directly, so you do not store the matrices. You compute an approximation of these per when you need them. So you trace array, you hit something, then you collect the photons in some radius, and that gives you the basis functions here. So it's really this kernel that is in that radius. Yeah, and I think this concludes it. Questions?
I've got another question.
Yeah.
There was another technique that was rather popular in the late 2000s to early 2010s called point base. Like, I mean, it's like global illumination.
You mean instant radiosity?
No. So they would generate a point cloud, like, of the scene, and they would use that to calculate like GI.
I don't know. I haven't heard of it. But I mean, whether you use a point cloud or whether you use a triangulation of your scene, it's not that important, at least for GI. You just need a way to reconstruct a surface set M, and you could use your point cloud to somehow do that. But it's not something that really, I don't think that's, at least as far as scene representation, that doesn't really affect you in terms of this formulation here.
Sorry to intervene. I think that Gabe's probably talking about micro rendering. It was
about what?
The micro rendering. It used to be a really popular method in some publications. I guess Dr. Young Coates published some papers about it, but I really haven't seen anything about it. It's probably what Gabe is talking about.
I haven't read it, so I cannot say anything about it.
Oh, that's fine. It's probably a finite element method, just like radiosity in instant radiosity.
I mean, a lot of methods, even if people don't realize it, even path tracing falls into path guiding falls into this framework, where what do you do in path guiding? You discretize your scene, and then you discretize the directions, and then you keep coefficients for each of these cells. Well, these are your coefficients, and your basis functions are based on your discretization. So that's path guiding. Photon mapping, once again, you drop some photons on your scene, so these are your coefficients, and then you choose, so you intersect your scene, and then you build. Once you intersect your scene, you build your kernel with which you want to blur, so you build your basis functions on demand, but it's still in the same framework. Now, path tracing is also in the same framework if you pick as basis functions Dirac deltas or reproducing kernels. So it's the whole thing. You can basically cast any technique, I think, in light transport in this framework. It's a bit involved though. What also? Yeah, density estimation, irradiance caching techniques. Mostly anything I can think of that deals with light transport, you can cast into this framework and then just pick the right basis functions and recover the technique. And then by also adding a specific solver, you get like all of these different methods that you can read about here. Other questions?
Well, I have a question. It's really not involved, but the random walk we've been reading about until this point in the book, and
Are you talking about the random walk that they are talking about here, or?
Yes. Yeah. I mean the random walk in this chapter 6.
Okay, so you mean let me find that. So you mean, where is that? So you mean that? Yes.
Yes, that's where the authors even go about and talk how you could estimate survival of a particle or absorptionness of a particle, and how you contribute. So, is it somehow related to metropolis light transport? I mean, not really metropolis light transport, the original paper, but I have some experience implementing a paper once, and there was the same experience of tracing a candidate, and he really talks about a candidate particle in this case in the chapter 6.
No, but
And
you
you
have the
check
same. You have the same thing in photon mapping, where you say, okay, I can terminate something. So terminating something early is not something specific to metropolis light transport. Terminating or even the opposite, splitting a particle into two or three, this is simply a variance reduction technique where it says, okay, if this path costs a lot but brings too little for the computation time, well, just terminate it. There's no point to waste computation time on parts of the integral that are not important, and vice versa. If I know that a part of the integral is important, well, I can split my particle in several ones. So split my array into, let's say, 10 or whatever. But so what they have in the book here, as far as stochastic Jacobi goes and random walk, is really one estimates each bounce separately. Maybe I can find this. I actually have that in the previous thing. And the random walk versus the Jacobi iteration is exactly a part in here that, where is that? No.
in the book, it really seems that it turns out that the random walk method is inferior to the stochastic one. I mean, and the Jacobi one, as the authors really make it
See,
clear.
that's the problem with these papers. Even the Jacobi one, it works under some assumptions. If I violate those assumptions, I can make the random walk method better. So what they mean to say there is that for the general assumptions that we made, like that are generally made in practice, yes, Jacobi is better. But if you make different assumptions, well, it doesn't hold anymore. So it's not that easy.
Oh, I see.
Where was the? I wanted to give exactly the example of what it means, what the random walk does as opposed to Jacobi. But where is that? So random walk acts a lot more similarly to what you do in path tracing. But do I have that? Okay, I have it here. So if you remember in the previous discussion, last week, we had the flux. So what we wanted to estimate from the measurement equation was the sum over all bounces over the estimators. And now you could write this in two different ways. You could sum over bounces and average in each dimension, or you could compute the whole path and then average over the paths. Well, this is the difference between stochastic Jacobi and random walk. Stochastic Jacobi is doing this. It's doing the average per dimension, then computing the next average for the next dimension, then the next average for the next dimension. So it's breadth first search. The random walk is like in path tracing. You trace the whole path, so this thing here, and then you average with the next path and then with the next one. Do you get the idea?
Yeah. It's like it's going really deep, bouncing a lot before moving to another.
Yeah. So this is more similar to path tracing. This is just Jacobi, as in how you would solve a linear system with Jacobi. Though they do it stochastically, in the sense that what's different to standard Jacobi? Well, you don't have your matrix. You compute your rows of the matrix on demand, and you estimate those rows stochastically with samples that you estimate how many samples you want to allocate per row. So your rows are approximate of the matrix. Yeah.
Okay, well, that's really good. Thank you.
Other questions? Yeah, this was a bit involved because, well, it involves finite element methods, but the good thing is the rest of the chapters don't really rely too much on it. I guess something to note was their terminology about shooting and gathering. So shooting would be you take your light sources and you shoot from those particles, and gathering would be you have your your elements, and you shoot from those some kind of importance. So it's exactly the one-to-one relationship to light tracing versus tracing rays from the camera. So that's the shooting versus gathering. I don't think. Yeah, so this hierarchical refinement here in clustering, this is really just adaptive finite elements, or you can even think of multigrid for preconditioning solvers, etc. So it's just known techniques that were tweaked a little, and then people wrote a paper about that. Yeah. I guess that concludes it. I've added some resources from the last discussion. So the first one is the dissertation of Lessig. You don't need to read that unless you care about the math and how finite elements relate to everything and reproducing kernel Hilbert spaces, stuff like that. Then I added a link to vertex connection and merging, which is an algorithm for mixing photon mapping with bidirectional path tracing, but this thing here is extended to volumes. You can find a similar thing called small VCM, which is not for volumes. I've also added some links to path guiding because, I mentioned that you can also think of these approximations of the rendering equation with finite elements. This is used in path guiding, so you can see the links here. And there's also some good lectures, and not specifically on Radiosity, that you can find here. Maybe you'll find them interesting, and they're pretty easy to follow, I think, also, if you want to have something extra. Which thesis doesn't go into Radiosity, so you can't see that here. There are some books cited in the current book, but I would just recommend to maybe avoid Radiosity, because well, it's outdated. Second, there's a reason it's outdated. The reason is that there are too many assumptions made, as mentioned, about the radiosity formulation. Now, if you go to the rendering equation and photon mapping, that would probably make more sense. So why pick an inferior method? Radiosity would probably be good only if you are concerned mostly with speed, I guess. Like stuff like instant radiosity, but that's pretty ancient, and at the moment you can even do some real-time path tracing with newer GPUs. Maybe just to mention what I'll focus on in the next chapter. So the next chapter finally includes bidirectional path tracing and metropolis light transport. I'll mainly focus on bidirectional path tracing and light transport. The others, yes, I can, I guess, discuss them a little bit, but probably I would focus on this, and the code would focus also on this to show you how to combine multiple estimators with multiple estimators for the bidirectional formulation with multiple importance sampling. So that's it from me. If there are no questions, feel free to go. Thank you for the attention.
Okay, thanks.
Thank you.
All right. Thank you very much.
Thank you.
Thank you.